guys active for a little bit. Calculators out. Calculators out. I want you guys to find, as a group, you can totally work together. Find for me the button that relates to exponential functions. I want you to find the one button. I guess there could be a couple. But there's a button you don't even have to go to a menu for that has to do with exponential functions. I want you guys to take 60 seconds to think it through and be like, Chris, go ahead and move over next to Joe. That way you guys can kind of, like you and Joe and Lauren can kind of collaborate. Just one over should be good. Okay. Talk it out. Pause. Turn to each other and say, what do you think? You guys are so silly. It's okay. Whoever doesn't have a calculator, let them see yours. What do you think? The one button that's not in a menu. There are a few options, I suppose. There's a total of 3 that aren't in menus that have to do with exponential functions. 1 you do not have to hit second for. The other 2 you have to hit second for. 1 is outright, and the other 2 are second something. All right, we've gone quiet. We're going to see if you guys are right in 1 second. First, let's fill in some blanks. Last chapter, we were talking mostly about, I'll put it this way, mostly about what we could call algebraic functions. Mostly what we could call algebraic functions, and now we're moving into transcendental. Oh, that's way too long for that blank. Transcendental. Did I get it? Transcendental. Transcend and then ending in dental. So exponential and logarithmic. We do have something called trigonometric functions that some of you guys remember from last year. But that's not coming until chapter 4, 5, 6-ish. I think the book has another word for the algebraic functions. Is there another name for it? Oh, never mind. Nope. They just call them algebraic too. Okay, so we have algebraic functions, and then we have transcendental functions. So the algebraic are all the different polynomials from constants, linear, quadratic, and all the rest. And then the rational functions, the polynomial over a polynomial, f over g. But now we're going to exponential and logarithmic. Pause. Before we go any further in chapter 3, don't you guys have a reflection from the last test? Yeah. Go find it. Go find it. What was on the back of that reflection? What was the brain teaser? There were 2 different ones. One was like a short baby one, hopefully. Hopefully it was an easy one. One was a little bit longer. On the top were the puzzle ones, right? On the bottom, what was the bottom one? Otherwise known as a Sudoku. Didn't we have another reflection we never turned in? Did we ever turn in the other reflection from before? Go find it. We had one from the chapter 2A, 2.1 to 2.4 quiz. I think a lot of you might not be ready to turn in the one from Friday. I think the puzzles were a little bit harder. So I'm going to actually not collect the harder one from you yet, the chapter 2 one, because I just saw a lot of blank Sudokus. But let's go to the other one, the one where you were trying to find the missing part to the triangle, right? And then the easier Sudoku. Chris, can I hold it up real quick so you can see? This one with the triangle. This is from the 2.1 to 2.4 quiz. And the easier Sudoku on the bottom. Okay, how do you play Sudoku? Because the directions are there. Oh, the directions are there. That's okay. The directions say each row has to have the numbers 1 through 9. The second rule says each column has to have the numbers 1 through 9. And then the last one says each bold box has to have the numbers 1 through 9. Here's the trick. Each row can only have it once. Each column can only have it once, it meaning each of the numbers 1 through 9. And each box can have it only once. So, for those of you that are looking at it, let's try to fill in a blank. I sadly don't have a copy. I do. There is a reason we're talking about Sudoku, not just because some of you need to learn how to do it for the harder one, let alone the easier one. Some of you need to finish up the reflections. How many of you didn't know how to play Sudoku before you got this handout? Okay. Maybe I won't take either one until tomorrow. Does that sound good? I think just a few of you guys need to learn how to play Sudoku first. I'm trying to find, where's my file? Test. There we go. All right, hold on. You might see more this year, and right now you have 2 different ones. Oh my goodness, you guys see the answer keys? I went really fast. View page width. Okay, so for example, some of you will find these fun. This one is super, no. It's pretty easy, and here's why. Do you see how there's only one box missing in this row? There's only one number that this can possibly be. Why is it a 2, Salma? Because no other 2. That has to be a 2. But since that has to be a 2, there can't be a 2 anywhere else in here. So I know none of these are 2s. But I'm going to go looking for something else that needs a 2. So this row has a 2. This row has a 2. Can't be in either of these anyway because this box already has a 2. So this row has a 2. That row has a 2. This row does not. But why can there not be a 2 either of these? The box already has one. Why can't these be a 2? The box already has one. Oh, that has to be a 2. So I have a 2, I have a 2, I have a 2. I have a 2 in this row. I have a 2 in that row, a 2 in that row. No 2. Well, I know that neither of those can be 2. Maybe that can be 2. Oh, yeah, no. That's why this one's easy. So then this one must be in order for this row to be able to have one. Does that make sense? And then this row has a 2. Okay, all my 2s are filled in. If this was like an online one, it would be like ding, 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 you're done. Like the 2s are done. So then we go looking for 3s and 4s and 5s. Question. Would this game be very fun if you didn't know any of the rules? Because then you would just be putting in probably like single-digit numbers and be like, there you go. Right? There's no competition. There's no game. There's no like figuring out the answer, right? Puzzles or games aren't fun. They're making up some sort of objective in order to make a game. Otherwise, well, there's no point. If you can do anything and everything with no objective, no end goal, no way of winning, then it's done. Okay, pause. I know. Put the reflections away. Play with the Sudokus tonight. Make sure to at least get this one done. We have a couple kids that haven't taken the test, so maybe I'll give an extra day on the harder one. The harder one is the one from Friday. Just borrowing. I think this one's pretty hard. Unless you think, how shall I say? I'll say. Anyway. This one you have to think outside the box. Ways as they appear. Otherwise, it's impossible. You just have to think about that. I chose not a very easy one. I think I just chose an easy one. But who knows? Maybe medium and is coming. Play with Sudokus a little bit tonight. But let's talk about why I just took time to help you with the brain teaser on the reflection sheet for Chapter 3. Chapter 3, the whole chapter, which we're starting in 3.1. We are going to be preparing, training, strengthening you, teaching you skills for the hard puzzles at the end. And if you don't learn the skills, you won't know the rules. You won't know the objective. You won't know how to get to certain levels, I could say. My video gamers, in order to play a video game, don't you at least have to know the basics of what's going on? But then, if you want to pass a certain level, don't you maybe go to YouTube or what's that one website where it's just gamers that are like recording themselves and how to... Thanks. Don't you start like actually going deeper trying to get farther or stronger or better or, I mean, I don't know. I'll just stop talking because my ignorance will start to show. But anyway, long story short, whether you're more of a puzzling kind of person, like logic puzzles, brain teasers, whether you're more of a video game kind of person, whether you're just like just give me like a soccer ball and let me just be competitive, or a football. Let me do it that way. I don't really like all the other stuff. Whatever it is, this chapter is preparing us for the hard puzzles, the hard problems, the hard levels at the end. And we have to train you. We have to remind you of things from the past. We have to teach you and make sure you're good at certain skills all along the way. So everything we're doing is basically getting you prepared for the puzzles at the end. And section 3132 says, hold on, let's just teach you the players. Let's just teach you the main components. And so one of the main components are exponential functions. And exponential functions, as you guys see from the title of chapter 3, exponential and logarithmic, he's one of the main players. He's one of the main types of functions that we'll see. So let's talk about him algebraically first of all. Let's talk about his equation. Who is he? Well, exponential functions are the guys with constants as bases and variables as exponents, or we could say powers. Exponential functions have constant bases and variable powers. There are some special logarithms too that are used more than others, but we're not just trying to get to know the special ones, we want to know all of them. So to that end, 2 to the power of down here for the example isn't necessarily a super special one that you're going to see all the time, but he is an example of a constant as a base, 2 is the constant, and a variable as the power, x. So if you were to get some sort of problem where it's like, hey, the function is 2 to the x, and then figure out the function value at negative 3.1, we could actually just go into old school. Plug it in, function notation. And if we plugged it in, we would find f of negative 3.1. We're doing the substitution over here. We would plug it in. Negative 3.1 would go in the exponent. Does anybody have, just real quick, like a mental estimate of what this should be around? Let's see. Ooh, decimals. I like the 8. I don't like the negative because the negative power does what? So we could say this should be approximately inverse, reciprocal. So 1 over who? The negative, remember, is the 1 over, and then the 3.1, well, 2 to the 3, as Jason already said, is about 8. And then Matthew was going further and saying, hey, I think I know the decimal to that. I think that's 0.1666666, right? Yeah. Okay. But is that exactly that? No. Well, how do you do 2 to the power of 0.1? We use our calculator. Did you guys find the button that I was referring to that is crucial for exponential functions? Not in a menu? Caret. Good. 2 to the power of. The caret was the one that did not need the second button and did not need a menu. Now, is there something cool in the math menu that might help you with exponential functions? Not really. There's a special one for a radical, for a root. But there's not really a special one for exponential. So the caret is actually going to be super, super necessary. And we could plug in negative 3.1. Or we could do, oh, that didn't work. It didn't get in my caret. 2 to the power of negative 3.1. Or we could have done the fraction form to remind ourselves of what was going on. That's not what I wanted. Sorry, alpha y equals. There we go. We could have done the 1 over 2 to the positive power of 3.1. That might remind you of what's going on. But there we go. But either way, was it approximately 1/8? Yeah, it was pretty close. So instead of 0.1666666, it's 0.116629, yada, 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 yada. So we'll go ahead and say, if we were doing the decimal form and not just the approximation, 0.117. That would be 3 decimal places. So you guys, go find me letter B. What would the function 2 to the negative x be when evaluated at pi? Huh. Do you guys back Matthew up? 0.113? To find the pi button in your calculator, have to use the caret button. Technically, I suppose I should use the approximate, but it's a much, 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 much better approximation. Okay, give me a thumbs up if you say yes, 0.113. Okay, I got a few. Thanks, guys. Now here's the weird thing. Why were those two so close to each other? Weren't they two totally different functions? Same base. Okay, so that's kind of important. Same base. Pi is 3.14, so that's approximately 3.1. But wait, that's negative and that's positive. So when you plug them both in, you're plugging in 3.1-ish to a negative exponent, which is doing a 1 over for both. So this one instead is approximately 1 over 8 as well. Why? Because it'd be 1 over negative 2 to the 3-ish, 8-ish. Yeah. So they were both approximations of 1/8, just they came from two different directions. Sort of. So, but the big thing is, yeah, they both had the same base, and their power was about the same after plugging in. Okay, exponential functions. Constants down below, variables up above. So when you plug in, you're not plugging in down, you're plugging in up. You're plugging into the power itself. Now, graphs. Two main things today. The equation, the function itself, which we just talked about, and then the graph. So basic graph of an exponential function. Have you guys ever heard, I don't know where you would have heard it, maybe in like a sermon illustration or a teacher in class or some sort of like financial analysis on the news or something about exponential growth, growing exponentially? It's talking about growing really fast because exponential functions are one of the fastest growing functions. Well, if it is growing. The sad thing is about functions, with a quick transformation, as fast as it's growing, it could be falling. There could be some life comparisons to that. People that tend to have super high highs can also have super low lows. But exponential functions. Just the most basic one, let's go ahead and just use y equals, keeping it general, a to the x. There are some things that I actually can be specific about, even though the base isn't specifically determined. I haven't made it a 2 to the x, or an e to the x, or a 10 to the x, or a 17 to the x. Just an a to the x. There are some things I can be specific about. For instance, I can make a little baby table, which we do with functions that we're not super familiar with. And there are 3 special points for any exponential function that we can actually start with. And if you remember chapter 1, section 6, parent functions, square root of x, x squared, absolute value of x, 1 over x. There were these parent functions that got transformed the next section. We talked about how it can be really, really helpful to have just a few set points to work off of. Shift the point, or multiply the y of the point, or multiply the x of the point. So some points for this one could be when x is negative 1, when x is 0, and when x is 1. What happens if x is 0? Anything to the 0 power, any positive integer to the 0 power is going to be 1. And if you're wondering, well, it's kind of specific about the anything, the only thing that is not 1 when raised to the 0 power is 0. 0 to the 0 power is not 0 or 1. It's something that we called indeterminate. It's undefined, but how is it undefined? That's a trippy one. That's a calculus question. But anyway, you can try it in your calculator. 0 to the 0 should say error. But anything else to the 0 power, always 1. So I can say as long as a is not 0, which it shouldn't be, because if it's 0, it's a really boring function. It's like 0, 0, 0, 0, nothing, 0, 0, 0, 0. Okay. Every other function is going to have I am so sorry, 0. 0, comma 1 as its, oh, hey, y-intercept. Every exponential function, if it hasn't been shifted, or reflected will always go through 0, 1. But what happens if you plug in 1? What's a to the 1? Just itself. So if it's 2 to the x, then that's going to be 1, 2. If this is 17 to the x, it's 1, 17. If this is whatever it is, it's just going to be a. So when x is 1, it's going to hit at a. Wait, so think about that. If it's 2 to the x, it's going to be 1, 2. If it's 17 to the x, it's going to be 1. So what's going to happen to the curve as the base goes up? It's going to get steeper or be growing. Vertical stretch, you could say that. It's going to get steeper. But what's going to happen if I had the base being like 1/2? It's going to be vertical stretch, and it's going to get flatter. So the higher the base, the steeper the curve, the faster the growth. The lower the base, the flatter the curve. What am I missing? -1. Why am I going to write 1 over a? A to the -1. A negative power is a reciprocal, so it's going to be a to the 1, but down here in the denominator. So I could also go ahead and show -1. Those are the 3 representative points that we're going to use for this guy's parent function. So let's go ahead and fill in more characteristics of the graph. Domain. Well, you guys answer me. How left does he go? All real, sure, but how left if we're doing intervals? Good. How right? Good. How low does it go for range? Good. Some of you might not have realized it yet, but if you graph it and keep on like moving the x-min lower and lower, it's going to get closer and closer until the pixels give out and say, I can't go any closer, and it just stops. But in all reality, as far as what's theoretically happening, it's getting closer and closer and closer. So 0 is the low, but I can't include it, hence the parenthesis. It's a horizontal, it's a horizontal asymptote. Why? Well, if it was -10, 1 over a to the 10th, it's just going to keep on getting smaller and smaller and smaller, and sorry for you guys, smaller and smaller and smaller and smaller, but never hitting 0. You can never raise something to a power and get 0. Strictly monotonic. Oh, we never finished. Sorry. How right does it go, or how up does it go? My bad. Good. It's just going to grow and grow and grow. Strictly monotonic. Have you ever had a teacher or like watched a movie where the person in it was very monotone? They was just talking like this the entire time, and it got kind of boring and people were falling asleep. It's usually like in a scene of a movie where they're like, oh my goodness, this person is awful, right? Monotone. Only one, not level because it's not flat, only one behavior. Strictly monotonic means only one behavior. What is this guy doing from left to right forever? Rising. Yeah, so we say it's only increasing or strictly increasing. And so if he were to get flipped, what would he be doing? A vertical flip? Yeah, he'd be strictly decreasing. Exponential functions only go one direction. And then continuous just means that you would never have to pick up your pencil in order to draw him. There's no vertical asymptote breaking him up, no hole, no domain problems. You might want to put that under continuous, no domain problems. So you could always just say domain is all real numbers. Now logarithms, they have problems, but it's okay. That's 3.2. Joe.
Actually, you can't raise
No. Exponential function, a is not allowed to be 0. Yeah, but thanks for bringing that. Technically for exponential functions, a itself, the base, is never considered to be 0 or a negative number. You could have a negative in front. The exponential functions, a is technically a number greater than 0. But good idea, Joe. So once we have the parent graph, and then we say, oh, you know what? Stuff can happen. Now, more stuff can happen than what's up here. But this is just a quick reminder of the basic things that you'll see. You might see a vertical shift. That would be adding a constant outside of the exponential guy. You can kind of see the exponential guy right there with his little argument up there. So adding outside of that would be a vertical shift. Subtracting inside of that will be our horizontal shift. And we just talked about A, the base. That can, like Joe was saying, that can be a vertical stretch of another exponential function in the sense of making it steeper or making it flatter if the base changes. Across the x-axis, quick reminder, if it's flipping this direction, that's an up-down flip. That would be a vertical flip. So just reminding you guys real quick, if it's a vertical flip, you're going to have a negative outside the exponential function. So it's actually going to be like a negative times the exponential function. Not a negative number being raised, but a negative on the outside. And then if you wanted, or if you needed, or if you were supposed to do a horizontal flip, you would see that negative inside, like up in that power, up in that exponent. Yeah. As far as like where it's supposed to be. It's just going to look differently because it's this weird exponential guy. And that would be a horizontal flip across the y-axis. So with those reminders, we can take somebody like, oh, did you find the other two buttons that had to do with exponential functions that needed the second? One of them was above the ln button, and one of them was above the log button. Above the ln button, second ln is e to the power of. That's an exponential function, a very, very special one actually, because e is a pretty important number. If you don't know who e is, you could either do that, e to the x button, and raise it to the 1 power. You could do that. See who he is. It's called the natural number. He's used in so many different things because he models a lot of natural growth and stuff in finances to do with compounding interest. But coming back, e is pretty important. But long story short, I could graph the parent function of e pretty easily because I know his intercept. His intercept is going to be 0, 1, just like everybody else. I know his point when x is 1. It's going to be 2.7-ish because that's who he is. So that's 1e, so 2.7-ish. And then I also know negative 1 is going to be 1/2-ish, a little bit lower. Yeah, between 1/2 and 1/3, a little bit closer to 1/3. Because then I'm going to have negative 1 and 1 over e. It's a horizontal asymptote. He's strictly increasing. Okay, that would be my basic function. But what would I do if I had this transformed guy who has 3 plus? All the y's need to add 3. So I could take this point, 1, 2, 3, shift up. I could take this point and shift up. Ooh, that'd be 0.7-ish, 0.7-ish, 0.7-ish. Shift up 3. This point, 1/2-ish or 1/3-ish, 1, 2, 3. I could even shift my horizontal asymptote, which is pretty cool. I could shift him, 1, 2, 3. And that helps, the horizontal asymptote helps a lot as far as getting that picture and getting that graph. That horizontal asymptote is helpful. And then if you were to have something like this guy, oh man, 2 flips, horizontal and vertical. I could take each of these points and say I have to flip it horizontally, flip the x sign, and vertically flip the y sign. And maybe with these points it would actually flip it horizontal and flip it vertical. Flip it horizontal doesn't go anywhere, vertical. Maybe using these points, though, will make this a little bit easier. The vertical asymptote, flipping vertical doesn't go anywhere, so that's kind of boring. But if I were you guys, I would get your 3 representative points before you go doing transformations to the basic function, like who's there underneath all the extra stuff. Does that make sense? Okay. And that'll make it a little bit easier. So the last thing that we didn't get to talk about is this thing called the 1-to-1 property. I'm going to zoom in on it because it's actually really easy. So it's okay that we don't have tons of time left. Because this guy says if you can make the bases match, then you only have to look at the powers. If you can make the bases match, you only have to look at the powers. So as you guys are writing down that 1-to-1 property, I'm going to take 64 down here and say, wait a minute, who is this guy? There's 2 8s, and each 8 has 3 2s. I can rewrite this to be 2 to the 2x and 2 to the 6th. This, according to my 1-to-1 property, in order for me to solve, I can actually kind of ignore the 2's and say, hey, the bases match. Sweet. So 2x has to be 6. This is only possible because this function passes the horizontal line test, but we didn't go deep into the theory as to why. We're just going to say, sweet, this is nice. Make a match, solve. How do we make this guy match? I mean, 125 is going to be 5 cubed. But it's 1 over says negative exponent. And check it. If I can make it a negative exponent, now do my bases match? So remember, negatives are going to be really helpful in order to flip things that seem, well, he's up and he's down. We'll make it a negative exponent. And then all of a sudden, life isn't too bad. You guys think you can do 1-to-1 property? I think so too, but you might need to use some factoring. Why didn't the bell ring? Did I miss it?
No, on chapel days, like the bell's like always off.
Usually, you guys can get out of here, sorry. Third period usually rings, guys. Thanks for the extra 35 seconds.
I know like the first bell rings and then the second period so it doesn't.
Yeah, and that's until chapel. I think they forgot to turn them back on.